Reinforcement learning has achieved remarkable success in robotics, where it was trained to race drones, navigate quadrupeds, and solve Rubik's Cube with a 5-fingered arm. Nowadays, it's common belief that RO can solve any task given enough data, which is usually considered a bottleneck. However, we argue that even when given infinite simulation data, state-of-the-art methods are still incapable of finding the true optimal solutions to complex continuous control tasks. This is what we investigate in our recent work, where we explore learning optimal policies through contact. In reinforcement learning, we're usually interested in optimizing the objective of cumulative reward by taking iterative gradient steps. One way to accomplish that is via zero-order model-free gradients. These methods have one key property: they do not require assumptions over the dynamics, which is enabled by the policy gradients theorem. It's impressive that they work well with minimal assumptions, and these types of methods are widely considered to have solved complex tasks, but are also known to be sample inefficient, requiring a lot of data to train. Model-based methods directly address this limitation by assuming the model is known or learned. This allows us to train via analytical gradients by backpropagating for the model. Although this addresses the sample efficiency issue, we are yet to see such algorithms that can match the raw asymptotic performance of model-free methods. In this work, we focus on addressing this and also challenge the common conception that model-free RO can solve all tasks given sufficient data. Unfortunately, when applying first-order methods, we quickly run into one issue: the real world is not always differentiable. A recently popular way to deal with this is through differentiable simulation, which usually utilizes a contact approximation model. For our work, it's imperative to understand how this affects learning. To do that, we investigate a very simple soft Heaviside function, which we approximate via Monte Carlo samples. From basic calculus, we know the true expectation of this function and its gradient. When the number of samples is limited, first-order gradients exhibit high bias, while zero-order gradients maintain a relatively good level of accuracy. This result is not great for first-order methods, which promise sample efficiency, yet are inaccurate under a small sample size. Under standard first-order assumptions of known model and reward, we showed that for a bounded policy and reward function, we can derive an upper bound for the first-order gradient bias. Looking at the right side of the equation, BR and BPi are easy to bound and do not present an issue. However, the gradient of the dynamics is difficult to bound. The more realistic we make the contact approximation, the higher the gradient norm. Furthermore, the longer the horizon is, the larger the bias. Our key idea is to roll out a model-based policy until stiff contact is encountered. We find that this alleviates the bias issue, making first-order gradients more accurate. Since we can obtain these contact gradients directly from the simulator at no additional cost, we can create an algorithm which has a dynamically adaptive horizon. Using the short horizon Actor-Critic approach as our base, we propose Adaptive Horizon Actor-Critic, or AHAC for short. It uses the same basic Actor-Critic architecture, but instead of using a fixed horizon, it adapts it dynamically based on specific task and the stage of training. The algorithm consists of 3 main stages: policy rollout, actor training, and critic training. Our key contribution is the use of a constraint objective function, which uses the same primal as Shack, but adds a constraint to ensure that the norm of the gradient of dynamics is below threshold C. From this objective, we extract the dual problem and optimize it directly to train our actor and also adapt the horizon using Lagrange coefficients. Finally, we train our critic using the same TD lambda objective like Shack, but now train it until convergence to account for a continuously changing horizon H, and also use a double critic. We evaluate our proposed approach on a suite of robot locomotion tasks. We compare it against its predecessor, Shack, the popular model-free baselines PPO and SAC, and against SVG, another model-based methods, which uses a learned dynamics model. Investigating the results on the popular AND task, we find that AHAC outperforms all baselines in terms of asymptotic reward. Since we're mainly interested in comparing against zero-order baselines, we normalize all rewards by the maximum achieved by PPO. Even though AND is widely considered a solved task, we find that AHAC achieves 51% more rewards than PPO, even if PPO is left to train for 3 billion time steps. Qualitatively, AHAC achieves more optimal and natural-looking behavior than PPO. We also run experiments on the classic tasks such as Hopper, a real robot such as Animal, the popular humanoid task with 21 degrees of freedom, and an alternative muscle-actuated version with 152 degrees of freedom. The aggregate results suggest that AHAC outperforms PPO by 40% across all tasks. From the score distribution, we can see that even in its worst case, AHAC still performs favorably against baselines. To find out more, please visit our website.